When you hear the word transformer these days, you probably think of those incredible AI models that are changing everything. But today, we're going to talk about the original transformer. It's a device with zero moving parts, invented way back in the 19th century, and it's been silently and reliably powering, well, pretty much every single part of your modern life. To really get why this invention was such a revolution, we have to rewind the clock, back to the dawn of the electrical age. Because you see, they were facing a massive power problem. So back in the 1880s, you had Thomas Edison's power grid, which ran on direct current, or DC, but it had a huge fatal flaw. See, to deliver power at low voltages, you need incredibly high currents. And over any kind of distance, a ton of that energy just disappeared. It was lost as heat. It was like trying to fill a bucket at the end of a super long, really leaky hose. Just incredibly inefficient. And this set the stage for what we now call the War of the Currents. You had Edison backing DC, but then you had Nikola Tesla, who came along with a totally different idea, alternating current, or AC. And AC had a killer feature. You could easily change its voltage. The key that unlocked that incredible potential, the one device that made AC the undisputed champion for sending power over long distances, was the transformer. So what is this world-changing device? Well, the real beauty of it is in its brilliant simplicity. Let's take a look at its truly elegant design. I mean, look at this. What you're seeing here is basically the whole machine. It's a static device. That means no gears, no pistons, absolutely nothing moves, so nothing wears out. It's just two coils of wire, a primary one for the input, a secondary one for the output, and they're both wrapped around a shared iron core. That's really it. First up, we've got the primary winding. Simple enough. This is the input side. It's the coil that gets the electrical energy from whatever power source you're using. And then you've got its partner, the secondary winding. This is the output coil. It's the one that delivers the newly transformed energy to whatever device you've got plugged in. And the thing that links them both, the iron core. Its only job is to be like a super efficient highway for magnetic energy, guiding it perfectly from the primary coil over to the secondary one. It's usually made of all these thin laminated sheets, which is a clever trick to stop energy from being wasted. Okay, so here's the wild part. We have two separate coils of wire that aren't even touching each other. So how does the energy jump from one to the other? Well, this is where the physics gets really cool. This is the magic of induction. All right, here's how it all goes down step by step. First, alternating current flows into that primary coil. Now, because AC is always changing direction, it creates a magnetic field that's also constantly changing, growing and shrinking. This magnetic field travels through the iron core, and when it washes over the secondary coil, it induces a brand new voltage. It's this incredible process where one coil's changing field magically creates a voltage in a totally separate coil. We call that mutual induction. And this really gets to the heart of its genius. The two coils are completely electrically isolated. They don't share any wires at all. The energy is transferred almost wirelessly, just through this invisible pulsing magnetic field. It's just an amazing piece of engineering. So, here's the crucial takeaway. The whole trick depends on a changing magnetic field. That's the secret ingredient. And that's why transformers only work with AC. If you tried to hook one up to a DC battery, you'd just get a steady, static magnetic field, and nothing would happen. No change, no induction. The magic just isn't there. Okay, so we know how it works, but its main job isn't just to move power, it's to change it. So let's look at its two big moves, stepping voltage up and stepping it down. And the secret to doing this is almost shockingly simple. It's all about something called the turns ratio. Basically, the voltage you get out is directly related to how many turns of wire are on the secondary coil compared to the primary coil. It's a beautifully simple and, most importantly, predictable relationship. This breaks it down perfectly. In a step-up transformer, you just put more turns of wire on the secondary coil. That increases the voltage, but there's a trade-off. The current goes down. And a step-down transformer, it does the exact opposite. Fewer turns on the secondary means you get less voltage, but more current. The total power stays about the same. You're just trading voltage for current, or the other way around. All right, let's tie this all together and see how this plays out in the real world, from the massive power grid that lights up our cities to the little gadgets right on your desk. This is why the transformer is just so important. At the biggest scale, you have these huge substation transformers. Power gets sent across the country at incredibly high voltages to cut down on energy loss. These giant transformers then have the critical job of stepping that voltage way, way down to much safer levels that can then be sent out to all of our towns and homes. But it doesn't stop there. You are literally surrounded by them. That power brick for your phone or your laptop? Inside is a little step-down transformer, taking the high voltage from your wall socket and turning it into the low-voltage juice your device needs to charge up safely. They're in your TV, your doorbell, countless devices that just make modern life possible. So there you have it. No moving parts, no software, just 2 coils of wire, a piece of iron, and a fundamental principle of physics. The transformer is truly the silent, indispensable workhorse of our modern world. It solved the great power problem of its time. Which leaves us with a pretty big question, right? As our own energy needs continue to change, what incredible invention will be the transformer of our future?